Hello, welcome to Seshi's Online Maths Tutoring. We are looking at a mock paper, question 1. A fair coin and a die feather are thrown together once. Using a table of all possible outcomes, find the probability of obtaining a prime number in a tail, no tail and no multiple of 3. So let's take the table of all possible outcomes. So the table is we having to match the outcomes of a coin to the outcomes of a die. So the outcome of a coin is just head and tail, and the die should produce 1, 2, 3, 4, 5, and then a 6. Okay, so these are the outcomes. So you have head 1, head 2, head 3, head 4, head and a 5, head and a 6, tail and a 1, tail and a 2, tail and a 3, tail and a 4, tail and a 5, and then tail and a 6. So this is the table of possible outcomes. We are asked to use that to find the problem of selecting a prime number and a tail. A prime number and a tail. So which of them is the prime number and a tail? So tail 2 is one of them. We can have tail 3, and we can have tail and then a 5. There are 3 in number. So problem of you having a prime and a tail should now be 3 out of the total outcomes 1, 2. You count the head 1, head 2, head 3 up to the tail 6. They are 12. So you can reduce that, and that's 1 out of 4. Anytime you have a fraction of that nature which is reducible, you reduce it. Now the I no tail and no multiple of 3. So the 2 should happen at the same time. If you have head 1, it has no tail, it has no multiple of 3. If you have head 2, it has no tail and it has no multiple of 3. If you have head 3, it has a multiple of 3, so it doesn't qualify. If you have head 4, it has none of the 2. If you have head and a 5, it has none of the 2. Then now if you look at the tail 1, tail 2, tail 3, they all have tails, so they don't qualify because they say no tail. So the probability of you obtaining a no tail and no multiple of 3 is going to be 1, 2, 3, 4 of that. Out of our outcomes 12, and that is 1 out of 3. And that ends our work for question 1A. Now let's move to question 1B. The set B and R are subsets of the integer universal set U, such that B has to do with composite numbers, R odd numbers, and U X is such that 5 is less or equal to X, less or equal to 15. First, let's list the elements of set U. 5 is such that X is such that 5 is less or equal to X. So all numbers that are that 5 is less or equal to. So 5 is part 6. And we are saying the numbers should also be less or equal to 15. So we end up at 15. Now we want our B. Don't forget B and R are subsets of U. So there shouldn't be any elements in set B which cannot be found in U. Likewise R. So B, which is composite numbers, ideally simply means composite numbers form the set U. So we look to our set U. What are composite numbers there? Composite numbers are numbers with more than 2 factors. 6 is 1, 8 is 1, 9, 10, 12, 14, and 15. Now R, which is having to do with odd numbers. Don't forget that's also odd numbers in the set U. We have 5, we have 7, we have 9, we have 11, we have 13, and we have 15. Numbers which are which are not divisible by 2, which means that when 2 divides them, there would be a remainder, and it should be from the set U. So that is why we limit our scope to the set U, because of the statement B and R are subsets of the integer universal set U. And the first I says that we are going to find B intersection R. What is intersection? It has to do with elements that appear in all the sets. So if you see an element in B, you see the same element in R, and that makes up BI intersection. 9 is 1. If you watch again, we can also find 15. So this 2 gives us the B intersection R. The next is R union B complement. Complement of a set has to do with elements which are not in the set but they are in the universal set. So what sets complements are we looking at? R union B. So first we must find R union B. So what's R union B? Elements in R at the same time in B, but then we don't want repetition because the set do not have its members repeated. So we arrange. We have 5, we have 6, we have 7, we have 8, we have 2 9s, we just write 1. We have a 10, we have 11, 12, we have 13, we have 14, and then we have 15. Right. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now we are going to look at R union B complement. Elements which are not in R union B but they are in U. If you watch carefully, all the elements in R union B are also in U. There is none left. So that particular answer is going to be an empty set, or you can also use the null set, and the two both will work as the result. Let's take the last question, that is question number C. So question C is asking you to find the product of 3x minus y and 3y minus 2x. 3x minus y and 3y minus 2x. To find the product. So if you find the product, one is multiplying the other. So I can take the whole of this to multiply each of what is in the other. So I take 3x, multiplying everything here to 3x, multiplying 3y minus 2x. And I take the next, which is minus y, multiplying 3y minus 2x. 3x times 3y is 9xy. 3x times 2x is 6x squared. Y times 3y is 3y squared. Negative times negative is positive. Then y times 2x is 2xy. I look through to see if there is any common term. Yes, 9xy and 2xy. So they have the same variable part, xy, xy. So therefore they are common. So we can add them. 9 plus 9xy plus 2xy is going to give you 11xy. You add the coefficient 9 and 2. The rest, there is nothing common. And I bring it as such. And that becomes the answer for question number 1C. Bye-bye.